Let's give it up for Leonardo.
So it's me again. I'm going to give you a quick introduction about reinforcement learning. In particular, I want to talk about OpenAI and OpenAI's gym. So a little introduction about myself. I worked for a few companies. I was working for the New York Knicks as a data scientist, not as a player. I was working for Justgiving. I can see some colleague here. I'm currently lead data scientist in Badoo, and we are hiring, so if you want to send us your CV. I'm also a contractor for the European Commission, and I have a training company. I'm going to do a training in November. That's enough about me. Quick overview about what we're going to see today. You're going to have some basic definition of what reinforcement learning is, and see some applications, and then hopefully if we have time, we're going to have a little demo. Quick question, how many of you have heard about the reinforcement learning? Can you raise hand? Everyone? How many of you have used reinforcement learning? Okay, quite a few people. Nice. Yeah, just a quick overview to see where reinforcement learning sits. Well, we can divide machine learning in these three categories, or four, it's arguable, but let's focus on these three. We have supervised learning, and that's probably what you're most familiar with, when you have inputs, outputs, and you try to create a model that is able to reproduce this relationship. And the idea is that hopefully with if you didn't overfit with new inputs, the algorithm is going to be able to produce the correct label or the correct value if you're predicting like the stock market price, or if you're just scoring some new data. You have your input, you use your model, and you get the labels that you want. There are a lot of applications about supervised learning, and we have an example here. Quite popular now, deep learning methods to extract information for images. So here we have an image, and the algorithm is able to tag every single component of the image. Then we have unsupervised methods. They're a bit less common than supervised learning, and the good thing is that we don't need labels for those, and it's something that sometimes is very handy, because getting labels from data can be very expensive and time-consuming. So unsupervised learning is only try to find the structure and patterns in our data set to find a way to cluster our data. And then we have reinforcement learning. Reinforcement learning works in a different way. We don't have inputs, we have an agent that performs some action on the environment and gets a feedback. It's a little bit like if you leave a toddler on a carpet and he's trying to walk, he's gonna do at the beginning just random movements, and then with the time he's gonna understand what is good and what he needs to do to be able to stand up and to walk. And this is because the environment gives a feedback, the agents take the feedback, and based on that he perform an action. But let's have a quick look on applications. There was a very famous algorithm, AlphaGo, that was able to beat a lot of Go masters. This image is when I think probably the most famous game when he played against the world champions in Go, and he was able to defeat a human, which was something that a lot of experts thought was not possible at this stage, and so. Some people say that this was like the Sputnik moment for other countries like China to start investing massively in AI, because they realized that some companies are really advanced. If AlphaGo wasn't enough, they started AlphaZero. AlphaGo was trained also with real games, so just human playing Go. AlphaGo Zero was just trained from scratch with other algorithms and was able to actually outperform AlphaGo. Reinforcement learning can be used in robotics. You can say that, for example, a mechanical arm can learn how to pick up an object without being taught that he needs to do that. We just define a reward when the object is picked, and the algorithm will try to take the actions to maximize his reward. There are a lot of applications. It's using text summarization engines and dialog agents, which are the classical bots. Is potentially also used for finding policies to treat health problems and health issues. Actually, I don't know of actual implementation of this because I know the healthcare system is quite delicate with these things. But it's used also for stock trading and scheduling. In general, it's used to learn how to take good decisions when to achieve a specific goal, when you don't know the environment and you don't have a clear policy. If you think about what you do when you're playing a game, is that you're looking at the screen, you get an idea of the environment, and based on that, you took an action. Maybe you shoot at the alien, or you move left and right, and the game will give you a reward. And our reinforcement learning algorithm is able to do a similar thing. In particular, this is an actor-critic model. And the very interesting part is that nobody told the agent that he needs to kill the alien. Sorry about the NASA guy. No aliens were armed here. It was just we just left the agent do some random moves, and with the time passing, he understood that shooting and hitting an alien will give him points, and being shot by an alien will lose points. So it took he learned basically how to win the game with just this reward function. You can do a lot of things with reinforcement learning. From one observation, you can do a 3D rendering of the object, and this is particularly useful for scenes. Imagine you have a picture from your childhood and you are able to recreate all the space around you, and maybe use a virtual reality kit to immerse yourself in this. We are not there yet, but there's some research around it. Particularly, these are generative Q networks. I'm going to share the slides. I'm going to give you some links to go through. Something I find really interesting. In particular, the first link is about a bot playing Doom, and actually playing it much better than me. Yeah, you can go through it and think they're quite interesting. But let's go back to our problem. So, as I said, we have an agent that needs to interact, that needs to learn a way to accomplish a goal. We can model this as a Markov decision process, where an agent, time t, receives a reward and a new status from the environment. So it just gives an idea of how the world looks like. In our game example was the screenshot we saw. And the agent, based on that, will perform an action. Then the environment, given the action, will give you a new reward and a new state in the next time step. It's quite easy to do this in OpenAI Gym. In practical, you have quite a few environments you can play with. I really like the Space Invader Atari, but there is Sonic, Doom, and a lot of others. And so this is what you see, and this is what the algorithm is able to see. It's just able to see these metrics of blocks. Some of them will be occupied, some of them will be not. And soon, well, not that soon, but with training, you will learn the right action at what's the right action at the right time. He's doing this by receiving feedback from the environment. The feedback is the score. And his goal is try to maximize the overall reward that he's getting from the environment, which is tricky because if you pick the wrong reward, you can have an unuseful situation like this. The reward was just being alive. At every time step, our agent will receive +1. So he didn't learn how to win the game. He just learned how to stay alive. And then we have just a quick introduction about a couple of algorithms. I will have to go a bit faster, but I'm free afterward for questions. Some algorithms are trying to estimate the total reward at time infinite, basically. And they are doing this with the Q matrix. When they have the Q matrix, they use a policy to find out the best action to perform. In particular, we have this is the states, and this is the action that we can take. So if you are in state 1, we have this series of possible actions. If we use a policy like epsilon greedy, it means that we will choose more often than not the one with the highest reward, which is the action 5. But sometimes we'll pick a random action. And this is because we need to explore the environment and to actually populate this Q matrix. At the beginning, the Q matrix is all zeros, when our algorithm is like a toddler that doesn't know how to move and doesn't know how to stand up and walk. There are some examples of these algorithms, which is the salsa and Q learning, and they work relatively well for simple problems. But then we also have a value-based method. Value-based method, these are the value-based method where we have a policy that acts on top of a Q function, and the Q function, I will say, is the total amount of reward the agent is gonna get. It applies a policy on top, and it performs an action. The environments receive the action and gives the feedback to our agent, and the agent will update his Q function given the feedback. So if you receive a positive reward, he will modify his Q function, giving more reward to the particular action he took and the particular state he was in. So let's say if we are in status 1 and we pick action 5 and we receive a reward, we're going to increase that specific entry in the table. This has some problems. First of all, the Q matrix can be huge when you have a lot of states, and you might not want to explore all these Q matrix. So there are other methods, which are policy gradient methods, that don't rely on the Q function. They rely only on the policy, and they try to find a way to maximize the reward, as we are doing in neural networks when we are minimizing the error. So an example, we have our input can be the screenshot that is processed by a neural network, and the neural network as an output gives us a set of actions, actually a distribution of actions. This because if we change the action directly, like we're doing the Q method with the Q matrix, this might have a huge impact on our algorithm, because I say we take the feedback too seriously. So that's why we are using these action distributions, and what we are maximizing is the total reward given a certain policy and given a certain theta, which is the variable we can play with to maximize the reward. Policy-based methods are quite useful when we don't want a value function, for example, for simple problem like playing Atari games, but also to balance a pole and a card, for example, and they're stochastic by nature, so they don't need this epsilon greedy policy that we are putting into top. There are also some problems because if you put a wrong step size, the algorithm can be very tricky to learn. So you might not learn anything, and the progress is really slow because usually you are very conservative. There are few methods that are now used to kind of mitigate these problems. One is PPO, but we have a lot of research, and I encourage you to have a look on OpenAI blog where they post all their research. It's very interesting, and they use a lot of policy gradient methods. There's also something in between value-based methods and policy gradient methods. It's what is called actor-critic models, who are kind of marrying these two concepts. I'm not gonna talk about them now, just because we don't have much time. I would like to show you a quick demo. This is a policy gradient method using OpenAI. You can see it was able to learn how to balance a poll for a certain amount of seconds. And as you can see, the cool thing is that I don't need to code the environment because I'm just importing it from OpenAI. I only need to code my policy and my agent, and it's very handy because you can change the environment extremely in a very easy way. So what the takeaway I would like you to have here is that OpenAI is a really cool framework to play with, and you can learn a lot without having to invest a lot of time to create the environments. Policy gradient methods are very useful, and OpenAI is a great resourceful tool for these sort of applications. Yeah, just a quick reminder, I'm doing trainings. We'll be doing a 2-day course in November. It's about mostly deep learning, so not reinforcement learning, but I will send you the slide if you're interested. Also, if you want to have some more information about reinforcement and deep learning, I'm planning to do some articles. So if you want to subscribe, feel free to write us, or if you have any question, you can also write directly to me. Thank you very much.
Well, it's always inspiring meeting someone who's involved in so many things around AI, teaching, training, blogging, real business. That's brilliant. Has anyone got any questions for Leonardo? Where's my beautiful sister Naomi?
You just taken some stochastic. Yes, sorry for that, but about that modeling. So I just want to know, what are the tools for that kind of modeling?
Yes. So OpenAI also created a repo which is called Baseline. So if you go on their GitHub, you can find some pre-made code about a few algorithms. This is an excellent tool just to get started and to modify a little bit about their tool. What I actually had was just some custom code because I think it's good to run through it and explain it. It's something I prepared for ODSC. Last week I was presenting in their reinforcement learning. So that was actually from scratch and was only using OpenAI as an environment, while all the other code was just from scratch. But OpenAI baselines have a lot of very nice algorithms already spread.
Great stuff.
Colin Roy, I'm trying to find people who might be interested in teaching an AI how to play diplomacy. Diplomacy is a 7-player game in which negotiation is integral to it. So there's natural language processing and large numbers of people. There's an annual competition. The state of the art is quite poor. And so it seems that this would be a fascinating challenge problem. Do you know of anyone who might be interested in that?
Well, I don't know, but we can use this meetup to find more people to be interested. So if you guys are interested, please just write info and we can get together and. Yes, you can also have a talk on our meetup. Maybe we can do a conjoint one another time and get more people. It seems a very interesting topic.
Okay, we have a bit more diversity. Do we have a question from a female voice in the room? Do we have any other questions?
The gentleman back.
Thanks. I was wondering if you could just, because as I understand it, reinforcement learning has a model-free and a model-based, and you were describing the difference between the policy or the reaction-based agents. I was wondering if you could just give a little bit more information and also explain what the pi failure pi equation is in the map.
Yes. Yeah, it was a little bit of a challenge to put all the topics together. So yeah, I tried to just give a broad overview and not to go too specific. I guess you're referring to this this equation here, right? Basically, we have a policy theta. Theta is the parameter we can play with. If you think about it's basically the neural network we are trying to tune, and exactly as you would do with a normal image task, that you have some input and some set of actions that you get as a feedback. You are trying to use to find the theta that maximize the return. So it's just a way to navigate under the curve of the returns. And as in normal deep learning problems, this is a kind of a bit of a stochastic process. So it's just a way to explore the possible solutions to get the best action out of it. So as an output, you will have an action distribution, which will favor the one who's the most useful action at the moment, but is not giving a definite answer. So we'll not just give one simple action as a output. We'll give the best distribution and other distributions. So yeah, this is just saying that it's trying to find theta that is maximizing the total amount of rewards that you have under a certain policy pi. And the total amount of rewards can go from 0 to finite amount if you are talking about an episodic task. But if you have an infinite task like balancing the pole, this can go up to infinite. You just had to add a discount factor for each reward.
I think we're out of time.
We can talk later. Happy to. Thank you.
Okay, big round of applause for Leonardo.